Hello everyone. Hope everyone is well. Hope everyone has a safe place to stay. Okay, so I want to talk about the material today that's in section 4.2 and 4.3. We covered this material on the last day before spring break, but there were a lot of folks missing, and as kind of a test of the system that we're trying, I'd like to quickly go over that. So if you were in class on the last day, you may have seen a lot of this. I don't think all of it, but a lot of it. Um, the idea here is that I have on the screen here the slides, the regular slides that are on Canvas, and you might want to download them and follow along as we go through. The other thing that I have on the screen is that I can bring up. I can bring up. Oops. There we go. There we go. I can bring up StatKey, and so we can do a couple of sample experiments with StatKey. And then finally, I also have the ability to write on a piece of paper here that sometimes seems darker than other times, so I'm not sure that I'm going to do very much of that. Okay, anyway, back to the slides. So you'll remember that we spent a long time for hypothesis tests. We spent a long time on writing down the hypotheses. There are 2 points of view. One called the Null Hypothesis. Those are the folks who are in the seats at that Holiday Inn in Kansas City. Those are the folks who are skeptical but fair-minded. They're willing to believe that that the presenter is saying something that's true, but they have to be persuaded. So they're always saying that the nominal value is what they're believing until they're persuaded otherwise. The nominal value might be, for example, the current rate that the drug lowers hypertension by. And then the other folks, the HA folks, they're the folks who think that there's something happening in this study that's of interest. They want to persuade the folks in the seats. So in that Holiday Inn in Kansas City, the doctor in the front of the room is the HA point of view, and the folks in the seats are the H naught point of view. The doctor has to be able to say to those folks, look, if what you're saying is true, then my study, the study I'm presenting to you today, my study has a number that's so far from what you're predicting that it's not really credible. My study has only a 1% chance of happening, or a 1/10 of 1% chance of happening, or a 1/100% of 1% chance of happening. It's very unlikely, and so hopefully the folks in the seats will say, really, that unlikely? Okay, I guess my point of view is not really sustainable, so I'm going to change my mind. The percentage the doctor is saying, the 1% or the 1/10 of 1% or the 1/100th of 1%, that's called the p-value of the study. So in a study, the p-value is the chance, computed assuming that the null hypothesis is true, of reporting a sample that extreme. The thing is that about the p-value is the doctor hopes that the p-value is small. Because if the p-value is small, then it provides evidence against H naught. It will persuade people to believe what the doctor wants them to believe. A smaller p-value provides stronger evidence against H naught. If you say to the folks in the seats, look, supposing what you're saying is true, then my study has only a 1/10 of 1% chance of happening. Then the folks in the seats will say, really, that small? I guess maybe what I'm saying is, I guess it's mistaken. I guess I might have to change my mind. That is to say, we might have to reject the null hypothesis. Okay. In order to persuade people, the doctor then needs to come up with a small percentage. And in order to come up with a small percentage, the doctor has to be able to say, look, here's the distribution of all the possible samples, and my sample is way, way far out on this distribution. My sample is very tiny. So I want to illustrate that happening. So let's see. So suppose you want to test your friend for ESP by having them predict 100 coin flips. So of course, the null hypothesis, the nominal value, is that your friend has, in the long run, if they predicted not 100 flips but 1,000 or 1,000,000 flips, has a 0.5% chance of being right. The alternative hypothesis, the people who think there's something interesting happening here, are the people who think that no, my friend has a more than 0.5%, more than 50-50 chance of happening, more than 50% chance of being right. So that's the 2 points of view, and we spent a long time talking about how to write those down. So now you run the study and your friend gets 51 of the flips right. So you report a p hat of 0.61. Remember again the difference between the p's and the p hat. P hat is the sample number. P's are your friend's chance not in 100 flips, but in 1,000,000 flips. So the doctor wants to be able to say to the people in the seats, you want to be able to say about your friend, you want to be able to say that okay, I don't know what my friend's true percentage is because this is only 100 flips and we don't think we got it right. But I think that my friend is greater than 0.5, and the evidence I provide for that is the 0.61. So in order to persuade the people in the seats, what you need to be able to do is figure out, is 0.61 a quite unlikely sample, a sample so unlikely that it'll make them sit up and take notice, or is 0.61 just, people will say it's just a sample thing, you got a few extra flips, got a few extra heads, don't get excited, it's nothing. I still maintain that I'm right, and that would be failing to reject the null hypothesis. Okay, so of course what happens is we go to stat key, and I'll go to stat key in just a second, but what you see is that with the contention that that p is actually 0.5, we always assume the null hypothesis is true. With the contention that p is actually 0.5, we then get a distribution of samples. If we did this with paper bags, then it would take longer, but we'd get exactly the same picture. There's something like 1,000 paper bags here. So we get something that looks like a bell curve. Up here it is umbrella shape, down here it is bowl shaped. So people picked out lots and lots of samples, happens to be 1,000 samples. And we're going to say, okay, so 0.61. Is 0.61 so crazy far out that folks will say, really, 0.61 you got? That's hard to believe that could happen just by chance. I guess my contention that the true number is 0.5 must not be believable. Okay, let's try that in stat key. So let's see. I got to blank out and bring in stat key, and I go to I'm doing a hypothesis test, and we're worried about a single proportion. So here I go, clicking on test for a single proportion, and excuse me, I have to move things around here. A person sees that the null hypothesis is 0.5. That's what we think, and my friend got 61 out of the 100. I got 61 out of the 100 right. And of course I'm going to push the button, and there's lots of buttons I could push, but I'm just going to push 1,000 just to push. And you see there's 1,000 dots. It looks a little different than the one I had on the slides because this is random and sometimes it looks different. I'm asking, what's the chance of a 61 or more? Is 61 or more so crazy unlikely that it will make the people in seats change their mind? So 61 is out here on the right hand side, so I'm clicking on right tail, and I have to tell it to make it a 61. So 0.61 and say okay. And what you see is that Saki has made into red dots all the ones that are 61 or higher. And we're saying to the folks in the seats, the alternative hypothesis people are saying to the null hypothesis people, look, the chance of a 61 or more is pretty low. Turns out to be stat key says it's something like 2.5% chance. So there's only something like a 2.5% chance of seeing a 61 or more. And now we have to say to the folks in the seats, we have to say that the alternative hypothesis people have to say to the null hypothesis people that we think that's so unlikely, and so at that point then we're having a discussion about how unlikely does it have to be before you change your mind. So you see here that when I did it this other time, when I did the time that made it on the slides, it was only a 1.5% chance, and when we just did it live, we got a 2.5% chance. That's just simply because these things are generated at random. That's all it is. So we're not getting exact numbers, we're getting practical values, and this is a practical class, so that's all that we really care about. Okay, so same setup, but now your friend gets 81 right, and the computer is going to give you a picture that looks like the previous picture, except that 81 is completely off the charts. So if we compare 61, which had something like a 1 or 2% chance of happening, with 81, which has a 0% chance of happening, well, clearly the 81 is persuasive. People who think that the true number is 0.5, and you walk in there and say, here's this 81, are going to say to you, 81, if p were 0.5, then 81 would be basically impossible. So the fact that you observed an 81 makes me think that p must not be 0.5. So that's how we hope to persuade the people in the seats, by coming up with a number so unlikely. That's the p-value right there. That number is so unlikely that we'll say to the folks in the seats, what you're contending that the true value is 0.5, what you're contending can't really be believable because we observed something that had like a no % chance of happening. So you must be mistaken. And they'll say, okay, I guess we are mistaken. That's called rejecting the null hypothesis. Okay, so we're of course not giving the mathematical formula for the distribution of samples. Instead, we're simulating it by doing things on the computer. So that's called an estimated p-value or an empirical p-value. And I can get a 1.5 and you can get a 2.5. So that's an awkwardness with those numbers. But the reason we're doing them, the important part here is that we want to understand the argument that a person makes in a hypothesis test. And so we don't want to get into the formulas, where they come from, all that sort of stuff. We just want people to be able to understand the idea involved in a hypothesis test, and the rest is gravy. If you understand the idea, then the formulas and everything will all prove to be very easy. So idea first, that's what we're doing at this point. Okay, so here's another example of the same sort of argument. I have high school math students who study while listening to music compared to people who do not study while listening to music. So I have two hypotheses. The null hypothesis is that they get the same numbers, and the alternative hypothesis is that the people who listen to music get worse values on the math test than the people who study while it's quiet. And of course, I have to have some data to settle the question, and I got to enter that data somehow into StatKey. So when you do here, I'll go to the place in StatKey. There we go. When you go to StatKey, you are of course now working with a difference in means. I have the averages for those folks who study while listening to music, and the averages for those folks who study without headphones, and so that's two different means, and I'm looking for the difference between the two means, so this is the right place to click. Here I go. The null hypothesis is always going to be that the two numbers are the same. That if we didn't do this with 5 people or 10 people, instead if we did this with many millions of people, we would know the true numbers and they would be the same. Of course, I have to enter the data that I'm given, and you've seen this before. You just click here. It asks you to enter, for example, I would enter something like music, comma, music, comma, music, comma, and get down to all the music data, and then I'd enter, silence, comma, and get to all the silence data, but I'm not going to enter that. Okay, so back to the slides. And when I entered all the data, you see the samples here. When I entered all the data, the null hypothesis is that there's no difference between the two means. I get something like a bell curve. It's a little more complicated, but it's something like a bell curve. And I simply want to know, is the sample that we had on the previous slide, the difference between those two so persuasive that it would convince a person who thinks this to change their mind? So is the x1 bar minus x2 bar, which is at negative 3.6, it says over here, is the x1 bar minus x2 bar that I got in my sample so far out that a person thinks to themselves, well, I can't believe that this is the right number. So negative 3.6 is something like about there. And you say to yourself, is that so far out that I just can't believe that this is the right number, or is that a perfectly ordinary everyday sample? And you say, well, you happen to get one that's a little on the low side. It could be a little on the high side. It's nothing. So of course you ask StatKey, negative 3.6, left tail, ask StatKey to count those dots. StatKey counts them. Turns out that the p-value, the percentage of dots that are red, the chance of getting a sample that far out on this distribution is something like 7.9%. Small, but not tiny. Not small enough probably to persuade somebody that what they think is true is probably not true. So 7.9% is the p-value, and it's small, but it's not small enough. Okay, in that example, I clicked on left tail because it says mu1 is less than mu2, so I'm looking at a left, that's all. If it had said greater than, I would have clicked on right tail, and if it said unequal, I would have clicked on the other option. The other option there is two tail. So then the question becomes, at what point do you decide, at what point do you say to yourself, okay, the null hypothesis people are going to change their mind? Is it 10%? That if the sample is only has a less than 10% chance of happening that they change their mind? Or is it 5%? Or is it 1%? Is it 1/10 of 1%? So we call that the significance level. That's the point at which the null hypothesis people are willing to change their mind. If you produce a p-value less than the significance level, then we reject H naught. So if the p-value was 7.9 in the last problem, if the p-value is small, then we reject H naught. How small does that? How small is small? And that's just a convention. It turns out that usually in most social sciences, in many studies, that number is 5%. You call that alpha, just a symbol. That's all. Alpha, 5%. If the p-value is less than 5%, then in those sciences, examples like, say, education, psychology, economics, typically if the p-value is less than 5%, then we will reject the null hypothesis. That is to say, the people in the seats will change their mind. If, however, if the p-value is more than 5%, remember it was 7.9% in the previous example. If the p-value is more than 5%, then we don't change their mind, and that's called failing to reject the null hypothesis. So if the p-value is small, we reject H naught. If the p-value is big, we fail to reject H naught. The usual turning spot is alpha equals 0.5. Now there are some fields where we may agree on a smaller alpha. You might decide that you want to be a little tougher. If you manufacture heart valves, you want to be really, really sure that they're going to last 10 years, then you might say alpha has to be something like, not 0.5, not 0.1, but instead 0.0001. So that's a very strict criteria. Most studies don't have such a strict criteria. The alpha equals 0.5 is really quite common. So for example, just to take an example, suppose you want to publish in the Journal of Foot and Ankle Surgery. For whatever reason, you're a foot and ankle surgeon. So you open the Journal of Foot and Ankle Surgery up to the inside front cover, and it says basically, don't send us a paper unless the p-value is less than 0.5. So we won't publish a paper where the p-value is more than 0.5. So they're telling you, that they want you to meet that criteria in order to persuade the readers of the journal. So alpha equals 0.5. The criteria, the place at which you change your mind of 5% is very, very typical. So that gives us with four possibilities. If H naught is true, or if H naught is false, or either the study rejects H naught or the study fails to reject H naught. That's the four possibilities that can happen. Let's suppose, for example, that you're writing for the journal Foot and Ankle Surgery, and you're proposing a new surgery to fix strained tendons in shot putters. So it could be that your surgery is a good idea. It could be that your surgery is a bad idea. H naught is going to be that the present state of treatment is the right thing. HA is going to be that the present state of treatment is that the new state of treatment is better. So H naught is that the present state of treatment is the right thing. If the present state of treatment is indeed the right thing and your surgery isn't the right thing, if the present state of treatment is the right thing and your study comes to a conclusion that you should reject H naught, that's called a type 1 error. So the present state of treatment is the right thing, and you're persuading people to reject the present state of treatment to go with the new state. That's called a type 1 error. Of course, if the present state of treatment is the right thing and you fail to persuade people, then the study's actually done the right thing. You've come to the correct conclusion. The other possibility is that H naught is indeed false, that the new state of treatment is the thing your HA, the thing that you're trying to get accomplished, is the right thing to do. So the H naught is false, that people should reject the null hypothesis. If people should reject the null hypothesis and your study persuades them to, then that was correct. The other possibility is that H naught is false and your study fails to reject the null hypothesis because you just didn't come up with data that was far enough out to convince people. That's called a type 2 error. Suppose you think about a study of the new blood pressure drug, and the current drug lowers blood pressure by 25 points. Does the new drug do better? So our first group takes the new drug, and the second group takes the current standard. We might want to choose an alpha equals 0.1 for our criteria. We will only say reject H naught if we have a p-value of less than 0.1. What is this researcher worried about the most? And of course, what this researcher is worried about the most is that, in fact, they got a way off sample, and that the new drug is not better. In fact, it's a little bit worse. But by sheer happenstance, the sample comes out to be such that the recommendation is to go with the new drug, and that's the worst thing that could happen. You don't want that to happen. So were we to shift from alpha equals 0.1 to alpha equals 0.5, then it would be easier to reject H naught, because p-values like 0.2 or 0.3 or 0.4 would result in rejecting H naught. So a sample would have to be less way out to lead to this bad recommendation. So it would be easier to make a type 1 error. So that is to say, the significance level alpha, one way to understand what the significance level alpha is it's the probability of making a type 1 error. So if what you really don't want is you really don't want type 1 errors, that H naught is the right thing and you're persuading people to reject it. That is, people were currently doing the right thing and you're persuading them to do something different. That's really the worst thing you can do. If you don't want that, then what you want to do is you want to set alpha to be quite small, so that there's very small probability of making a type 1 error. In the social sciences, the trade-off is that usually you pick an alpha of about 0.5. And it's something like engineering, if you're worried about the tolerances on your chips or something, you might want to take alpha equals 0.1 or maybe even a smaller value. Okay, I think we're going to skip the last section just in view of trying to get things done here. So, whoops, hit the wrong button. So, so for homework, I'd like to ask you to look at it in section 4.2, which is on page, which is on page 281, section 4.2. I'd like you to look at Scale Builder 2, Scale Builder 3, Scale Builder 4, and Scale Builder 6. So again, that's 2, 3, 4, and 6. And we also covered some material from section 4.3. Section 4.3 is on page 296. So I'd like you to look at for homework Scale Builder 1, Scale Builder 2, Scale Builder 3, number 95, number 97, and number 101. And I'll remind you that the answers to the odds, or at least brief answers to the odds, are in the back of the book. Okay, then I think that brings us sort of caught up to where everybody in the room is in roughly the same place. I'll be sending emails out talking more about how we're going to proceed forward, but I'd like you to be trying those homeworks so that when I give you assignments to try at home and hand in, graded assignments, that then you're ready for them. Okay, and again, I hope everybody is staying well, and I hope that hope that everybody has a safe time at home. Okay, thank you.